time might not flow at all. We could be missing an entire dimension that holds the key to its mystery. This is not science fiction, but a real possibility emerging from the edges of physics. By the end of our journey, you will see time not as a river, but as a geometric secret woven into the cosmos. We will follow the clues from melting ice cubes to the echoes of the Big Bang, revealing how a forgotten dimension could explain why we remember the past but not the future. How do you feel when you think about the true nature of time? Heraclitus saw a river that never stood still, a world in constant, irreversible change. That ancient observation touches a mystery that has haunted thinkers for millennia. Why does time move only forward? Ancient civilizations often viewed time as a great wheel, turning in endless cycles of creation and destruction. Eastern philosophies embrace this concept, seeing the cosmos itself as breathing in and out across vast eons. But with the rise of classical physics in the West, a different picture began to emerge. Time became a one-way street. Isaac Newton framed time as an absolute and universal river, flowing at the same steady rate for everyone, everywhere. It was a majestic idea, but it left no room for explaining why the river only ran downstream. Then came Einstein, who shattered that absolute frame. He wove time and space together into a single fabric, where gravity could bend and stretch the flow of time itself. A clock on a mountaintop truly ticks faster than one at sea level. Yet even this revolutionary theory held a deep silence. Einstein's equations work perfectly whether time runs forward or backward. The laws of physics, at their most fundamental, do not point to a past or a future. So where does our powerful, daily experience of time's arrow come from? The answer began to emerge not from the cosmos, but from the steam engine. The science of thermodynamics introduced the concept of entropy, a measure of disorder. The second law of thermodynamics states that the total entropy of a closed system always increases. Ice melts in your drink, never reforming spontaneously. Smoke disperses in a room, never gathering back into the cigarette. This irreversible increase in disorder gave science its first physical arrow of time. Physicist Arthur Eddington later gave this idea its famous name, boldly stating that the arrow of entropy is the sole reason we remember the past and not the future. But this only pushed the mystery one step deeper. Why was the universe in such a state of low disorder to begin with? Every era, from the philosophers to the physicists, framed the problem with the tools they had, each revealing a new layer of the puzzle without finding its ultimate source. This long historical struggle sets the stage for our modern quest, forcing us to look beyond the familiar dimensions of space and time for an answer. Watch a single ice cube melt in your glass on a warm afternoon. The transformation is so ordinary we hardly give it a thought, yet it holds a profound secret. The puddle of water never gathers itself back into a perfect, frozen cube. This one-way street is our most direct experience of time's arrow, governed by a fundamental rule of the cosmos known as the second law of thermodynamics. This law states that in any isolated system, a quantity called entropy always increases. Entropy is simply a measure of disorder or randomness. A solid, structured ice cube has low entropy. The disordered puddle of water molecules, freely moving and mingling, has high entropy. The universe, it seems, has a relentless preference for mess. But why should this be? The answer lies not in some cosmic force, but in the statistics of unimaginably vast numbers. Think of a new deck of cards, perfectly ordered by suit and value. That is low entropy. Now shuffle it once. The order is slightly disrupted. Shuffle it 1,000 times, and the cards will be in a state of complete randomness, a high entropy state that is, statistically, overwhelmingly likely. There is only one way for the deck to be perfectly ordered, but an almost infinite number of ways for it to be disordered. The journey from order to disorder is a one-way trip, because the final destination is so much more probable. The physicist Ludwig Boltzmann was the first to truly grasp this statistical heart of entropy. He showed that the irreversible flow we perceive as time emerges from the blind shuffling of countless microscopic particles. The ice melts because the countless molecules within it have far more ways to be arranged as a liquid than as a solid. The process is not impossible to reverse, just so fantastically improbable that you would have to wait longer than the age of the universe to see it happen by chance. Boltzmann gave us a powerful explanation for why we remember the past and not the future. We remember the state with lower entropy. Yet this brilliant insight immediately raises a deeper, more troubling question. If a state of high disorder is so overwhelmingly probable, why did the universe begin in a state of such spectacularly low entropy? Why was the cosmic deck of cards ever in that pristine, ordered state to begin with? This is known as the past hypothesis, and it is a gaping hole in our understanding. The laws of physics do not demand a beginning of low entropy. They allow it, but they do not explain it. The thermodynamic arrow points firmly in one direction, but it cannot tell us why the arrow was ever knocked in the bow. This suggests that entropy is not the ultimate source of time's flow, but merely a consequence. It is a powerful clue that something deeper set the initial conditions of our cosmos, perhaps a structure hidden in the very geometry of reality itself. Our universe is flying apart, and this great expansion provides the second profound clue to time's mystery. Billions of galaxies are not simply drifting in a static void. Space itself is stretching, carrying them apart in what cosmologists call the Hubble flow. This relentless outward rush, tracing back to the Big Bang, gives us a cosmological arrow of time. The universe was born in a state of almost unimaginable heat and density, a singularity where the very concepts of space and time break down. From that initial moment, it has been expanding and cooling, evolving from a hot, simple plasma to the complex cosmos of stars, planets, and life we see today. This direction of cosmic evolution, from the hot and dense to the cold and diffuse, aligns perfectly with the thermodynamic arrow of increasing entropy. The initial low-entropy state of the Big Bang provided the fuel, and the expansion of the universe provided the mechanism, allowing disorder to steadily increase. Cosmologists like Alexander Vilenkin have explored how the very geometry and evolution of the universe might be intrinsically linked to this one-way flow. The expansion is not just a backdrop for time, it seems woven into its fabric, and this process is not slowing down. The discovery of dark energy revealed that the expansion is accelerating, pushing galaxies apart at an ever-increasing rate, driving the cosmos toward a cold, dark, and ultimately high-entropy future. This paints a clear picture, but it also presents a deep puzzle. What if the universe stopped expanding and began to contract in a theoretical big crunch? Would time reverse, with entropy decreasing and shattered glasses reassembling themselves? Most physicists believe the answer is no. The arrow of time, once established, seems locked in place. This suggests that the expansion of the universe is a symptom of time's arrow, not its ultimate cause. The real mystery is why the expansion began in that specific low-entropy state. This cosmological perspective forces us to look beyond the visible universe, beyond the equations of general relativity and thermodynamics, for an answer. The expansion of space itself may be a consequence of a deeper, hidden dimensional reality, a geometric structure that governs both space and time from a level we are only beginning to perceive. We remember yesterday with perfect clarity, yet the future remains a complete blank. This is the psychological arrow of time, the most intimate and undeniable direction we experience. Our minds are not passive observers of time's flow, we actively construct it. The philosopher William James described consciousness as a stream of thought, a continuous flow where one mental state blends into the next, creating the sensation of a moving present. Modern neuroscience reveals this is a complex illusion woven by our brains. Consider the feeling that time flies when you are having fun, or drags during a tedious wait. Your brain is not measuring objective minutes. It is compiling a story based on sensory input, attention, and memory. Central to this process is a brain structure called the hippocampus. It acts as a sort of mental time machine, allowing us to project ourselves backward to relive memories or forward to simulate future scenarios. This ability, known as mental time travel, is what gives our lives a narrative arc. Even puzzling experiences like déjà vu, that eerie sense of having lived a moment before, are likely glitches in this sophisticated memory system, where the brain momentarily mislabels a new experience as a past one. Yet this entire mental construction rests on a physical foundation. Every memory you form, every thought you have, is a biochemical event in your brain. These events are governed by the same thermodynamic laws that melt an ice cube. When neurons fire, they consume energy and increase the disorder, or entropy, within your own head. Your perception of time flowing from past to future may simply be your consciousness riding the wave of increasing entropy in your neural circuitry. This raises a profound question. Is the relentless flow of time we feel just a side effect of physical processes, a biological illusion crafted by evolution to help us survive? Or does our deep-seated perception of a moving now point to something more fundamental, a true temporal dimension that our minds are uniquely tuned to detect? Consciousness alone cannot be the source of time, for it is itself a process unfolding within time. The very fact that our internal arrow so perfectly aligns with the cosmic and thermodynamic arrows suggests a deeper connection. The mystery of time is not just in our minds or in the stars, but woven into the hidden geometry of reality, compelling us to look beyond the world we see. Einstein tore down the absolute stage of Newtonian physics, revealing a universe where space and time are not separate entities, but woven together into a single, dynamic fabric called space-time. In this four-dimensional tapestry, time is not a universal river flowing at the same rate for everyone. It is relative. Your experience of time depends entirely on your motion and your position within a gravitational field. This is the core of his theories of relativity. In special relativity, he showed that a clock in motion ticks slower than one at rest. The famous twin paradox illustrates this beautifully. If one twin rockets away on a high-speed journey through space and returns, she will be younger than her Earth-bound brother. Her motion through space literally slowed her passage through time. General relativity deepened this strange picture by introducing gravity not as a force, but as a curvature in the space-time fabric itself. A massive object like the Sun creates a depression in this fabric, and planets like Earth follow curved paths, not because they are pulled, but because they are rolling along the warped geometry of space-time. This warping also affects time directly. The stronger the gravity, the slower time passes. A clock at sea level, closer to Earth's mass, ticks measurably slower than a clock on a mountaintop. We do not notice this in daily life, but our technology does. The global positioning system must constantly correct for this effect. The satellites in orbit, experiencing weaker gravity, have clocks that run faster than those on the ground. Without these relativistic corrections, your phone's GPS would be off by several miles within minutes. Einstein himself grappled with the philosophical implications of his work. He came to believe that the division between past, present, and future is a stubbornly persistent illusion. This is the block universe concept, where all of time, every event that has ever happened or ever will, exists simultaneously in a static, four-dimensional block. From this God's eye view, your birth, your life, and everything else are all just permanent points in the cosmic structure. Yet this breathtaking vision creates a profound conflict with our lived reality. While his equations perfectly describe a universe where time is just another coordinate, they are completely symmetric. They work just as well if time runs backward. There is nothing in general relativity that explains why we can remember yesterday but not tomorrow, why cause always precedes effect. Space-time geometry can bend time, but it cannot give it an arrow. This is Einstein's unfinished revolution. His theory provides the stage, a magnificent dynamic fabric of space-time, but it offers no script for the one-way play we call time. The relentless flow we feel, the melting ice, the expanding universe, our very memories, all point to a reality that his four-dimensional picture cannot capture. To solve this, physics must venture beyond, into the quantum realm and perhaps into dimensions we cannot see, searching for the hidden mechanism that broke the symmetry and set time on its singular course. An electron can spin both clockwise and counterclockwise at the same time. This is not a theoretical fantasy but a daily reality in the quantum realm, a state known as superposition. Here, particles exist in a blur of all possible states simultaneously, a fuzzy cloud of potential that defies our everyday logic. This bizarre behavior lies at the heart of quantum mechanics, and it presents a direct challenge to our classical understanding of time. How can a sequence of events unfold if the events themselves are not yet decided? The act of measurement forces this cloud of possibilities to collapse into a single, definite reality. This is the quantum measurement problem. For pioneers like Niels Bohr, this collapse was a fundamental process, and the observer played a crucial role in bringing reality into being. This act of observation, from the fuzzy quantum world to a sharp classical fact, seems to introduce a powerful arrow of time. Information goes from being a set of probabilities to a single, recorded outcome, a process that appears utterly irreversible. Erwin Schrödinger famously illustrated the absurdity of applying this quantum weirdness to our scale with his thought experiment of a cat that is both alive and dead until someone opens the box. But if the quantum world is truly timeless, how does this definite sequence of before and after emerge? The key may lie in a process called quantum decoherence. Imagine a perfectly still pond. You can drop a single pebble and watch the clean, coherent ripples spread out. This is like an isolated quantum particle in superposition. Now imagine a torrential downpour. The surface becomes a chaotic mess of overlapping ripples, and any single pattern is instantly lost in the noise. This is decoherence. A quantum system, when it interacts with its environment, is like that pond in a storm. The countless collisions with air molecules, photons, and other particles instantly destroy its delicate superposition, forcing it to choose a single classical state. This continuous, irreversible interaction with the environment is what makes quantum probabilities solidify into the definite past we remember. It is the primary reason we never see tables and chairs in two places at once. Yet, this creates a monumental conflict at the very foundation of physics. In its standard form, quantum mechanics treats time as an external, absolute background, a stage on which the quantum drama plays out. It is a parameter that is simply there, ticking away independently. But Einstein's general relativity showed us that time is dynamic, a flexible part of the space-time fabric that warps and curves. How do you combine a theory where time is absolute with one where it is malleable? This clash is known as the problem of time in quantum gravity, and it suggests something extraordinary. Time might not be a fundamental ingredient of the universe at all. Instead, it could be an emergent property, a collective illusion that arises from the relationships between countless quantum events, much like the temperature of a gas emerges from the jostling of its molecules and does not exist for any single atom. This leads to a startling possibility. The quantum processes we see, from superposition to decoherence, might merely be symptoms of a deeper, hidden dimensional structure where the true nature of time is encoded. If time is not fundamental, what kind of reality lies beneath it, and what forgotten dimension holds the key to its flow. The clash between gravity and the quantum points toward a reality far stranger than either theory alone can describe. To bridge this divide, physicists turn to one of the most elegant and radical ideas ever conceived, string theory. It proposes that the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy called strings. In this symphony of the cosmos, the specific note played by a string, its unique vibrational pattern, determines whether it manifests as an electron, a quark, or a particle of light. The properties of all matter and forces emerge from these microscopic harmonies, but this beautiful symphony requires a much larger stage. For the mathematics of string theory to work, the universe cannot have only the three spatial dimensions we experience. It demands extra dimensions of space, perhaps 6 or 7 more, curled up into shapes so incredibly small that they are hidden from our view. Think of a garden hose stretched across a field. From a distance, it appears as a simple one-dimensional line, but an ant crawling on its surface knows it has a second dimension, a circular direction wrapped tightly around the hose's circumference. Our entire universe could be like that hose, with these compactified dimensions coiled into intricate geometric shapes at every single point in space, far smaller than any particle we can measure. As string theorist Greene has eloquently put it, the universe may be akin to a cosmic loaf of bread where our reality is just one slice, one surface of a far richer multidimensional whole. This framework is not just about adding more spatial directions. It provides a new geometric language that could finally unite general relativity and quantum mechanics. The way these extra dimensions are folded and curled determines the very laws of physics in our visible world, setting the constants of nature and the strengths of forces. And this is where the mystery of time finds a potential new home. If we can have hidden spatial dimensions, could one of them be fundamentally linked to the flow of time itself? Perhaps what we perceive as the relentless march of time is actually a manifestation of a deeper, geometric property of one of these forgotten dimensions. In this view, time is not a mere parameter ticking in the background, but a dynamic and physical entity, a dimension with its own unique curvature and structure, woven into the fabric of these higher dimensional spaces. String theory provides the mathematical playground where such a forgotten dimension of time could be rediscovered, transforming it from a passive stage into an active player in the cosmic drama. What we perceive as the relentless flow of time could be merely a shadow cast by a far richer, higher dimensional reality. Our universe might be a three-dimensional membrane, or brane, floating within a vast, higher dimensional space known as the bulk. This is the startling vision of Brane cosmology, a framework emerging from the depths of M-theory. In this picture, all the particles and forces we know are trapped on our brane, like waves on the surface of a pond. But gravity, uniquely, can leak out, spreading into the extra dimensions of the bulk. This could explain the perplexing weakness of gravity compared to other forces, and it even offers a compelling explanation for the dark matter that holds galaxies together. Physicist Randall and others have shown how a warped extra dimension could naturally account for these cosmic puzzles. But the most profound implication is for time itself. The forgotten dimension we are searching for may not be a spatial one at all, but a second dimension of time hidden within the bulk. Or it could be a spatial dimension with a fundamental, built-in asymmetry. Imagine a gentle slope running through the higher dimensional bulk. Our brane universe, embedded within this space, would naturally experience a preferred direction, much like a ball rolling down a hill. This inherent gradient could be what breaks the perfect symmetry of physical laws, ensuring that entropy always increases and that cause always precedes effect in our world. The arrow of time would not be written into the fundamental laws. but would emerge from this dimensional interaction. The melting ice cube and our fading memories are not driven by a law of physics that commands forward motion, but are instead the inevitable result of our brain's position and orientation within a grander geometric structure. This transforms time from a fundamental river into a secondary effect, a compelling illusion generated by our limited perspective. If this is true, then the deepest mysteries of our cosmos, from its birth in the Big Bang to the nature of consciousness itself, may be locked in the geometry of dimensions we have yet to perceive. The universe began with a whisper of perfect order. That initial state of spectacularly low entropy, the fine-tuned starting point for all of cosmic history, is the ultimate question mark hanging over physics. Why was the cosmic deck of cards ever in that pristine, ordered state? The forgotten dimension offers a breathtaking escape from this puzzle. It suggests our Big Bang was not an absolute beginning, but a transition, a quantum leap from a pre-existing state in a higher dimensional reality. Think of it as a bubble forming in a vast, timeless ocean. Our entire cosmos could have quantum tunneled into existence, a fluctuation in the deeper geometry of the bulk. This idea resonates with the visionary no-boundary proposal by James Hartle and Stephen Hawking, which removed the singular starting point of the universe by describing its origin in terms of a smooth, geometric shape, like the North Pole of a globe. There is no boundary, no sharp edge where physics breaks down. Introduce an extra dimension, and this picture transforms. The smooth geometry of the no-boundary proposal could be the shape of our brain itself, a surface with no edge, embedded within the greater bulk. The low-entropy beginning is no longer a mysterious initial condition slapped onto the universe, but a natural consequence of its birth from a higher dimensional state that simply has no past. This dimensional perspective also breathes new life into ancient cyclic models of the universe. Imagine our brain universe floating in the bulk, periodically colliding with a neighboring brain. Each collision releases immense energy, fueling a new Big Bang and starting a fresh cosmic cycle. In this eternal rhythm, the arrow of time is reborn with each new cycle, its direction set by the geometry of the collision in the higher dimensional space. The universe does not need to be specially wound up with low entropy at the start of each cycle, because the dynamics of the collision itself provide the necessary gradient. The profound implication is that the forgotten dimension makes the extraordinary seem ordinary. The fine-tuned initial conditions that have baffled cosmologists for decades emerge naturally from the deeper, geometric laws governing all dimensions. By providing a larger canvas, the extra dimension removes the need for a special beginning, weaving the origin of time's arrow directly into the fabric of a grander reality. This resolution of the initial conditions problem is a monumental step, pointing toward a framework where all forces of nature are ultimately united. The dream of a final theory, a single mathematical framework uniting all the forces of nature, has been the guiding star of physics for more than a century. We feel gravity's pull, we see the effects of electromagnetism, and we know the strong and weak nuclear forces bind atoms and power the stars. Yet these four forces remain stubbornly separate in our descriptions of the world. Unifying them would reveal a cosmic simplicity hidden beneath the apparent complexity. And the forgotten dimension might be the very bridge that makes this possible. This radical idea is nearly a century old. In the early 1920s, just as Einstein was reshaping our view of gravity, a little-known mathematician named Theodore Kaluza made a breathtaking proposal. He took Einstein's equations for general relativity, which describe the four-dimensional fabric of space-time, and rewrote them for a universe with 5 dimensions. The result was astonishing. The familiar equations for gravity were still there, perfectly intact, but an extra set of equations emerged naturally from the math. These new equations were none other than James Clerk Maxwell's complete laws of electromagnetism. Simply by adding one more dimension, Kaluza had unified two fundamental forces. Physicist Oscar Klein later suggested this fifth dimension was not a large, expansive one, but curled up into a fantastically small circle, far beyond the reach of any microscope. In this Kaluza-Klein theory, the electric charge of a particle is not some arbitrary property. It is simply the momentum the particle has as it moves through this tiny, hidden dimension. A particle moving in a loop around the tiny circle would appear to us as a charged particle interacting with the electromagnetic field. The geometry of the dimension, the size of that circle, directly determines the strength of the force. This was a monumental insight, showing that the laws of physics we observe could be dictated by the shape of unseen dimensions. String theory and its extension, M-theory, are the modern embodiments of this grand vision. In this framework, the different vibrational patterns of the fundamental strings, dancing through all the extra dimensions, manifest as the different force-carrying particles. One specific resonance of a string might be a photon, the particle of light and electromagnetism. Another, distinct vibration could be a gluon, which carries the strong nuclear force. The strengths of these forces, the so-called coupling constants that have been measured with immense precision, are not arbitrary numbers. They are fixed by the precise way the extra dimensions are folded and curled. The geometry is the law. Now, consider the implication if one of these forgotten dimensions is intrinsically linked to time. This would not merely unify forces in a static sense. It would weave the arrow of time directly into their fabric. Certain rare particle decays known to violate time reversal symmetry provide a crucial clue. In these processes, the sequence of events would look fundamentally different if time were run backward. This phenomenon, called CP violation, is a key ingredient for the existence of our matter-dominated universe. If the hidden dimension governing time has an inherent asymmetry, a kind of geometric twist, it could naturally explain why these interactions have a preferred direction. The flow of time and the unification of forces would be two sides of the same coin, both emerging from the deep geometry of the cosmos. This suggests that the forces which sculpt our reality, from the nuclear furnaces in stars to the chemical bonds in our bodies, are inseparable from the temporal dimension through which we experience them. The search for a unified theory is not just a quest to combine equations. It is a journey to understand why our universe has a past and a future at all. And this profound connection between force and time compels us to ask one final, transformative question. If extra dimensions shape the laws of physics and the flow of time, what would it mean to directly detect their hidden architecture? Space-time itself may be a grand illusion, a smooth surface that emerges from a hidden, churning reality far beneath. For centuries we imagined the cosmos unfolding on a static, four-dimensional stage, but the forgotten dimension suggests this stage is not fundamental. It builds itself from something more primitive. Imagine watching a movie on a high-definition screen. The image appears seamless and continuous, a perfect representation of a scene. But if you press your face against the glass, you see the truth. The picture is composed of countless tiny, discrete pixels, individually switching on and off. Our smooth, continuous spacetime may be exactly like that screen, an approximation that emerges from a vast network of fundamental building blocks. This is the radical promise of theories like quantum gravity and causal dynamical triangulation. In these frameworks, spacetime is not a given. Instead, think of a vast, shifting cosmic graph. At the highest energies near the birth of the universe, this graph is a chaotic soup of disconnected points, like a pile of raw pixels before they form an image. There is no space, no time, no proximity, and no distance in this primordial state. As the universe cools, these points begin to connect, forming links in an evolving network. The pattern of these connections, the architecture of the graph, gives rise to the geometry we experience. What we perceive as the distance between two stars is not a fundamental separation, but a measure of how many links you must traverse between their corresponding points in the underlying network. Even more profoundly, time itself emerges from the relentless, step-by-step evolution of this graph's connections. This is a deeply relational view of time, as physicist Lee Smolin has championed. Time is not a background parameter, but the expression of the changing relationships between the events that constitute the universe. The smooth, flowing time we feel is the large-scale average of countless microscopic, discrete changes in the quantum geometry. Much like the temperature of a gas is an average of the frantic motion of its molecules. No single molecule has a temperature, and no single event in the quantum graph has a flowing time. The forgotten dimension provides the ultimate substrate for this cosmic condensation. It is the higher dimensional arena in which this entire network of space-time pixels is embedded, the bulk that gives it structure and allows for its dynamic assembly. This resolves some of the most vexing paradoxes in physics. Consider the black hole information problem. General relativity suggests information swallowed by a black hole is lost forever, while quantum mechanics insists it must be preserved. But if spacetime is emergent, the information is not lost. It is simply stored in a different way, encoded in the intricate patterns of the underlying quantum graph within the higher dimensional bulk. The event horizon is not a destructive boundary, but a transitional layer where our familiar spacetime dissolves back into its more fundamental form. If this is true, then our deepest intuitions about reality are a convenient fiction. Locality, the idea that objects are only influenced by their immediate surroundings, is an emergent property. Causality, the unbreakable chain of cause and effect, is a compelling story that only makes sense in the smooth, classical limit of this deeper, more chaotic quantum world. We perceive a flowing now because we are large, composite beings, averaging over trillions of these discrete events every second. The river of time is not flowing through us, we are the flow. This redefinition of spacetime forces us to accept that the solid stage beneath our feet is a shimmering mirage, a collective dream woven from the hidden architecture of a forgotten dimension. A black hole is the ultimate vault, swallowing everything that crosses its event horizon. Not even light can escape its gravitational grip. But what happens to the information carried by the objects that fall in? According to the bedrock principles of quantum mechanics, information can never be truly destroyed. It might be scrambled, but it should, in principle, be recoverable. For decades, a fierce battle raged over this very question, a conflict that became known as the black hole information paradox. The great Stephen Hawking initially argued that black holes do destroy information. As they slowly evaporate through a quantum process, they radiate energy back into space. Hawking calculated that this radiation was completely random, a featureless hiss carrying no data about what fell in. If the black hole eventually vanishes, the information is lost forever. This violated the principle of unitarity, a sacred rule of quantum mechanics that demands the preservation of information. Hawking was so confident that he made a famous bet with physicists Leonard Susskind and John Preskill. Susskind fiercely defended quantum mechanics, insisting that information must be preserved, even if we did not yet understand how. The paradox seemed insurmountable. How could information escape from a prison from which nothing escapes? The forgotten dimension offers a breathtaking escape route. The key lies in the holographic principle, a revolutionary idea championed by Susskind and Gerard T. Hooft. It proposes that our seemingly three-dimensional universe, with all its rich content, might actually be a projection of information stored on a distant, two-dimensional surface. A black hole's entire interior, with all its swallowed stars and planets, could be encoded on its two-dimensional event horizon, the point of no return. The information never actually falls into the three-dimensional pit. It is painted onto the surface, much like the data on a Blu-ray disc encodes a three-dimensional movie. Extra dimensions profoundly enrich this picture. Our universe could be a three-dimensional brane, and the information falling into a black hole might not be lost at all. Instead, it could be transferred or leaked into the higher dimensional bulk, preserved in a geometry we cannot directly access. This idea finds a stunning expression in the ER equals EPR conjecture. It proposes a deep and elegant connection. ER refers to Einstein-Rosen bridges, better known as wormholes, which are tunnels through spacetime potentially connecting distant points. EPR refers to the famous Einstein-Podolsky-Rosen paper on quantum entanglement, that spooky connection where particles instantly influence each other across vast distances. The conjecture suggests that these two seemingly different phenomena are one and the same. Every pair of entangled particles is connected by a microscopic wormhole. This wormhole is not a tunnel through our ordinary space, but a shortcut through the extra dimensions of the bulk. Now, apply this to a black hole. When an object falls in, its information doesn't vanish. It becomes entangled with the Hawking radiation leaving the black hole, and this entanglement creates a wormhole link through the higher dimensional space, preserving the information. The forgotten dimension, especially one linked to time, could govern how this information is processed and retrieved. The arrow of time might be the direction in which information flows and is holographically reprocessed across these dimensional bridges. Leonard Susskind ultimately won his bet with Hawking, who famously conceded that information is, in fact, preserved. Resolving this paradox does more than just save quantum mechanics. It forges a direct link between the fate of information, the geometry of spacetime, and the very flow of time. It suggests that the cosmos operates like a colossal quantum computer, where information is never deleted, only transformed and transferred across the hidden architecture of reality. This solution to one of physics' deepest puzzles powerfully demonstrates that the forgotten dimension is not a mathematical curiosity, but a fundamental feature that could unify our understanding of everything, from the smallest particles to the darkest corners of the cosmos. Dark energy is not a substance but a symptom of our dimensional blindness. For decades, astronomers have watched in awe as distant galaxies recede from us at an ever-increasing pace, driven by a mysterious repulsive force that makes up the vast majority of the cosmos's energy budget. This acceleration is the universe's most dominant dynamic, yet its origin has remained one of physics' greatest enigmas. The forgotten dimension offers a radical reinterpretation, suggesting that what we call dark energy is not a new form of energy at all, but a geometric effect emerging from the hidden architecture of reality. Imagine our universe as a membrane adrift in a higher dimensional bulk. The energy density we measure as dark energy could be the subtle pressure of the bulk itself pressing against our brain, or the energy stored in the curvature of an extra dimension as it slowly evolves over cosmic time. This is not merely a philosophical shift. It is a concrete mathematical possibility explored in models like the Dvali-Gabadad's Porati-Brane world scenario. In this framework, gravity is free to leak into an extra dimension over very large distances. This leakage fundamentally modifies the force of gravity on the grandest scales, producing an accelerated expansion that perfectly mimics the effects of a cosmological constant, but without requiring one. The equations reveal that the observed strength of dark energy is not an arbitrary number, but is set by a fundamental length scale, the crossover scale where gravity begins to feel the extra dimension. If this hidden dimension is intrinsically linked to time, its influence becomes even more profound. The evolution of this temporal dimension, its gradual unfurling or shifting curvature, could be the engine driving the cosmic acceleration we observe. The arrow of time and the expansion of the universe would be two expressions of the same underlying geometric process. This provides a stunning connection between the most intimate aspect of our experience and the ultimate fate of the entire cosmos. Cosmologists studying these models point out that they naturally avoid the extreme fine-tuning problems that plague the standard cosmological constant. The energy density remains stable over time, elegantly matching observations without mysterious cancellations. This implies that the fate of the universe, whether a continued runaway expansion or a future phase transition, is written in the geometry of dimensions we have yet to directly perceive. Dark energy becomes a cosmic clue, a fingerprint left by the forgotten dimension, urging us to look beyond the surface of reality to understand the forces shaping its deepest rhythms. The universe's final act is not yet written. Cosmologists have outlined several possible endings, each a starkly different finale to the cosmic story we find ourselves in. The most widely accepted is the Big Freeze, a slow, cold death where the universe expands forever. Stars burn out, and all matter eventually decays into a thin, featureless haze. Alternatively, if dark energy grows stronger over time, it could lead to a big rip, where the fabric of spacetime itself is torn apart, shredding galaxies, planets, and finally atoms in a final, violent crescendo. A third, more dramatic ending would be the Big Crunch, where the expansion reverses and the entire cosmos collapses back into a fiery singularity. The ultimate fate hinges on a delicate balance between the outward push of dark energy and the inward pull of gravity. This is where the forgotten dimension steps in, not as a spectator, but as the director of the final act. The properties of this hidden dimension could dictate the long-term behavior of dark energy and the very strength of gravity over cosmic timescales. If the extra dimension is stable, our current accelerated expansion might continue steadily toward the cold, quiet emptiness of the Big Freeze. But what if this dimension is not static? Its geometry could be evolving, slowly shifting over billions of years. A gradual change in the way the dimension is curled or warped could cause dark energy to strengthen, pushing us toward the cataclysm of the Big Rip. Or it could weaken, allowing gravity to eventually regain the upper hand and pull the universe back together in a big crunch. This possibility breathes new life into ancient visions of a cyclic cosmos. Our universe could be a single episode in an endless series. Each big crunch would not be an end, but a transformation, a reset triggered by the dynamics of the higher dimensional bulk. The collision of branes or a quantum rebound in the extra dimension could fuel a new Big Bang, starting the cycle anew. In this eternal rhythm, the arrow of time is reborn with each cycle, its direction set by the geometry of the transition. As physicist Paul Steinhardt, a proponent of cyclic models, has suggested, the universe may have no beginning and no end, only perpetual renewal. The stakes of this dimensional influence could not be higher. A phase transition within the extra dimension, a sudden rearrangement of its fundamental geometry, could alter the very constants of nature. The strength of forces, the mass of particles, everything that makes our universe stable and habitable could change in an instant, launching reality onto an entirely new and potentially hostile trajectory. If the forgotten dimension truly governs time's arrow, its inherent properties might ensure that a reversal like the Big Crunch is impossible. The same geometric gradient that gives us a past and a future could lock the cosmos into a one-way expansion, forever favoring the heat death of the Big Freeze over a cyclical rebirth. This profound connection ties the fate of every galaxy, every star, and every atom directly to the hidden architecture of reality. The microscopic nature of dimensions determines the macroscopic destiny of all existence. The flow of time and the fate of the cosmos are not separate stories, but two chapters of the same epic, written in the geometry of a dimension we have yet to see. Pondering the universe's ultimate end inevitably pulls our gaze backward, toward the past, and raises a tantalizing, almost irresistible question. If the geometry of dimensions can shape the entire future of reality, could it also allow us to revisit what has already been? The classic grandfather paradox presents a logical nightmare. If you travel back in time and prevent your own grandfather from meeting your grandmother, you would ensure you are never born, making your journey impossible in the first place. This is more than a science fiction plot. It is a fundamental challenge to causality, the principle that cause must always precede effect. General relativity, in its pure mathematics, allows for pathways that could, in theory, become time machines. These are known as closed time-like curves, hypothetical loops in spacetime where an object could travel forward in time only to return to its own past. Wormholes, tunnels through the fabric of spacetime, could potentially be engineered into such a loop. Physicist Kip Thorne and his colleagues explored this very idea, demonstrating that the equations do not explicitly forbid it. Yet, the universe seems to conspire against such possibilities. Every proposed design for a time machine requires exotic matter with negative energy density to hold the wormhole open, a substance that may not exist or would be vanishingly rare. This cosmic censorship hints at a deeper protection mechanism, one that may be written into the forgotten dimension. The topology of the extra dimensions, the way they are connected and curved, could naturally eliminate closed time-like curves from being physically realizable. The higher dimensional geometry might simply not support the intricate twisting required for a stable time loop, rendering them mathematical ghosts without physical substance. This leads to a profound principle championed by physicist Igor Novikov. The Novikov self-consistency principle asserts that if time travel were possible, the universe would enforce a kind of logical inevitability. Any actions you took in the past would already be a part of established history. You could not change the past because your presence there was always meant to happen. Your attempt to interfere would be thwarted by seemingly random events, a slipping knot or a sudden distraction that preserved the timeline. In the context of the block universe, where all of time exists simultaneously, your journey to the past is just another fixed point in the higher dimensional structure. There is no branching, no alteration, only a single self-consistent story. Now, if the arrow of time itself emerges from a gradient in the forgotten dimension, this principle becomes a physical law. Moving backward in time would be like trying to swim up a waterfall, an endeavor doomed by the fundamental geometry of reality. The dimension that gives us a past and a future would inherently enforce a one-way flow, making retrograde movement as impossible as reversing the increase of entropy. Causality, the very backbone of our rational world, appears to be protected by the hidden architecture of the cosmos. The forgotten dimension acts as a guardian, ensuring that effects follow causes and that logic is never broken. This does not entirely eliminate the dream of time travel, but it radically redefines it. We might one day learn to navigate the currents of time, but we would be sailing with the flow, never against it. Explorers in a universe whose deepest laws are designed to keep the story consistent. These theoretical constraints are not just philosophical. They lead to tangible experimental tests. Could we detect the subtle signatures of this protective geometry in the behavior of particles or in the echoes of the cosmos? Deep beneath the border of France and Switzerland, protons race in opposite directions at nearly the speed of light. Inside the 27-kilometer ring of the Large Hadron Collider, they are steered into violent collisions, recreating energies not seen since the first instance of the Big Bang. Scientists are not just looking for new particles in the debris, they are hunting for something even more elusive, missing energy. In our familiar three-dimensional world, energy is always conserved. But if extra dimensions exist, energy could literally vanish from our reality, carried away by particles like gravitons that are able to escape our dimensional membrane and travel into the higher dimensional bulk. This signature of missing momentum is one of the most sought-after clues for the existence of a hidden cosmic architecture. The hope is even more dramatic. At these immense energies, the collider could, for a fleeting instant, create a microscopic black hole. Such an object would evaporate instantly in a shower of radiation, a clear signal of new physics. While we have not yet seen one, its potential discovery would revolutionize our understanding of gravity and dimensionality. These experiments are incredibly challenging, as noted by physicist Maria Spyropoulou, who describes the search as looking for a needle in a haystack, except the haystack is the size of a planet, and the needle might not even be there. Yet the stakes are so high that the search continues with relentless precision. Another telltale sign would be the appearance of Kaluza-Klein modes. Remember the tiny, curled-up dimensions. A particle moving through such a dimension can have different vibrational states. Much like a guitar string can play different notes, each vibrational state would appear to us as a distinct particle. This means there could be heavy, identical copies of every known particle, like electrons and quarks, but with vastly greater mass, echoes of their motion through the hidden dimensional geometry. Detecting one of these resonant heavy twins would be direct, incontrovertible proof of extra dimensions. If the forgotten dimension is specifically linked to the flow of time, the experimental search expands beyond colliders. We would need to look for a different kind of signature, a subtle drift in the very constants of nature. The strength of gravity or the fine structure constant that governs electromagnetism might not be constant at all, but could be slowly changing over cosmic time as the temporal dimension itself evolves. Astronomers are already performing these tests, analyzing the light from the most distant quasars to see if the fundamental rules of physics were different billions of years ago. A confirmed variation would be a seismic discovery, pointing directly to a dynamic, higher-dimensional fabric underlying our reality. On an even more intimate scale, physicists are probing the force of gravity at distances smaller than a millimeter. Why would gravity, which we experience as incredibly weak, be so feeble? The answer could be that it is not weak at all, but is simply diluted, spreading its lines of force into the vastness of the extra-dimensional bulk. In theories proposed by Arcani-Hamed, Dimopoulos, and D. Volley, some of these extra dimensions could be surprisingly large, not curled up at the Planck scale. If this is true, then at sub-millimeter distances, gravity should suddenly become stronger, deviating from Isaac Newton's famous inverse square law. Exquisitely sensitive experiments using tiny, vibrating cantilevers or precisely balanced torsion balances are now attempting to measure the gravitational pull between two objects separated by a hair's width, searching for that telltale strengthening of the force. These are the crucibles where speculation is forged into science, where the abstract geometry of the cosmos meets the uncompromising reality of data. Each experiment, from the colossal to the microscopic, is a probe sent into the unknown, seeking the architectural plans of a reality we have only just begun to perceive. And just as these tools push the boundaries of the very large and the very small, another technological frontier is opening, one that manipulates the fabric of reality itself. Optical lattice clocks are so precise they would not lose a second over the entire age of the universe. This staggering accuracy is not just for timekeeping, it is a direct probe into the fabric of reality itself. These clocks work by trapping atoms in a grid of laser light, creating an incredibly stable quantum metronome. If the forgotten dimension subtly warps the local flow of time, these devices could detect the minute variations, a temporal shimmer revealing the hidden architecture beneath our everyday experience. This is just one of the breathtakingly sensitive tools now being deployed in the search for dimensional reality. Far from the public eye, engineers are designing experiments that operate at the edge of the possible. To detect the fantastically weak signals of extra dimensions, they must first conquer noise. Laboratories are built deep underground, shielded from cosmic rays. Detectors are cooled to temperatures within a fraction of absolute zero, a cryogenic deep freeze that stills the jittering of atoms, allowing the whisper of a new physics to be heard. One such experiment is the holometer at Fermilab. It uses powerful lasers down two perpendicular 400-meter-long vacuum tubes, acting as the most precise rulers ever conceived. It is searching for a fundamental graininess to space-time, a hypothesized holographic noise that would appear as a jitter in the laser beams. This noise could be the pixelated flicker of the underlying quantum graph, the signature of a reality built from discrete bits of information projected from a higher dimensional surface. In space, an even more ambitious project is taking shape. The Laser Interferometer Space Antenna, or LISA, is a future gravitational wave observatory that will place 3 spacecraft millions of kilometers apart in a precise triangular formation. By monitoring the distance between them with laser beams, LISA will detect the ripples in spacetime caused by colossal events like merging supermassive black holes. But it could also sense something far more subtle. Certain models of extra dimensions predict a specific background hum of gravitational waves, a relic rumble from the early universe that would carry the imprint of the bulk's geometry. Another frontier is atomic interferometry, where clouds of ultra-cold atoms are used as exquisitely delicate test masses. By observing how these atoms fall in a vacuum, scientists can test the strength of gravity at microscopic scales, searching for the precise deviations that would signal gravity's leakage into a large extra dimension. Each of these technologies represents a monumental feat of human ingenuity, a collective effort to stretch our senses into realms we cannot naturally perceive. The physicists and engineers behind them, like those refining the sensors for the next generation of cosmic microwave background telescopes, often describe their work as a kind of cosmic listening. They are tuning enormous instruments to catch the faintest echoes from the dawn of time, echoes that might have bounced through higher dimensions before imprinting themselves on the oldest light in the universe. This technological drive does more than test abstract theories. It forces the creation of new capabilities. The extreme precision required for these experiments often leads to unexpected innovations, with potential spin-offs in computing, navigation, and materials science that ripple through our daily lives long before the fundamental mystery is solved. As we build ever more sophisticated devices to listen to the cosmos, we are not just seeking answers. We are reshaping our relationship with reality itself, forcing us to confront what it means to measure the immeasurable and know the unknowable. Every choice you have ever made feels uniquely your own, a testament to your free will. Yet the laws of physics seem to describe a clockwork universe, where every event is the inevitable result of what came before. This is the ancient philosophical war between determinism and free will, and the forgotten dimension throws a startling new light onto the battlefield. If the flow of time emerges from a geometric structure in a higher dimensional bulk, then our entire experience of reality becomes a matter of perspective. The philosopher Immanuel Kant argued that time is not an external reality, but a fundamental form of our intuition, a lens through which our minds necessarily perceive the world. He would have been fascinated by the block universe, where all moments in time exist simultaneously in a static 4-dimensional structure. In that timeless picture, your life is a completed sculpture, and free will seems like an impossible illusion. But what if both views contain a piece of the truth? The hidden dimension offers a profound synthesis. Imagine that the entire block of our spacetime is a single, fixed sculpture within the higher dimensional bulk. From that God's eye view, the entire timeline is determined. Yet, we are not beings who can perceive from that perspective. We are consciousnesses embedded within a single slice of that sculpture, moving through it moment by moment along a path defined by the geometric gradient of the extra dimension. Our journey feels like a sequence of free choices precisely because we are blind to the higher dimensional whole. The physicist Greene has noted that our sense of free will may be compatible with a deterministic underlying reality if we define it by the complexity of the decision-making process itself. This is the heart of compatibilism. Your choice between tea and coffee this morning was the result of a breathtakingly complex calculation in your brain, weighing memories, desires, and sensory inputs. That process is deterministic in principle, governed by the laws of physics playing out on our brain. But from your internal perspective, trapped within the flowing now, it was an authentic act of deliberation and choice. The forgotten dimension makes this coexistence elegant. The deterministic laws unfold in the bulk, setting the entire timeline, but the phenomenal experience of making a choice, of feeling the weight of possibility and the flow of time, is real and irreducible within our dimensional slice. This resolves the tension not by denying one side, but by showing they are descriptions from different vantage points. Causality itself is transformed. We perceive a strict chain of cause and effect because we are surfing a wave in the higher dimensional geometry. The cause is not just an event in the past, but a feature of the bulk structure that guarantees the effect in our future. This does not rob us of our agency, it relocates its foundation. Our conscious decisions are not magical interruptions of physical law, but they are the physical law manifesting as a complex, self-aware system. Your life is not a pre-recorded film you are forced to watch, but a unique and authentic path you are walking, even if the entire landscape already exists from a higher perspective. This is more than a physics problem, it is a deep metaphysical shift that redefines the self. The forgotten dimension suggests that the flow of time and the sensation of free will are two sides of the same coin, both emerging from our limited viewpoint within a grander, geometric reality. This realization echoes through our culture and our stories, challenging us to find meaning not in absolute freedom, but in the profound authenticity of our experience journey. Our oldest stories are a testament to our struggle with time. Long before physicists wrote equations, myth-makers were painting time as a great wheel in Hindu cosmology, endlessly turning through cycles of creation and destruction, or as a linear arrow in Christian eschatology, marching toward a final judgment. These narratives are not primitive guesses, they are profound intuitions about a mystery we are only now beginning to measure. The idea of a forgotten dimension governing time's flow finds a deep echo in this cultural heritage, resonating through the literature, films, and art that explore the fluidity of our reality. H.G. Wells, in his novel The Time Machine, framed time as a fourth dimension through which his protagonist could navigate, a concept that was radical fiction in his era, but prefigured the geometric view of spacetime that Einstein would later formalize. A century later, Christopher Nolan's film Interstellar visualized this explicitly, depicting astronauts navigating a higher dimensional tesseract, a structure where time becomes a physical space to be traversed. The film's scientific consultant, physicist Kip Thorne, noted that their goal was to never violate established physics, but to push its visual imagination to the very edge, showing how higher dimensions could warp our most fundamental experiences. This interplay between science and story is a two-way street. Indigenous cosmologies from the Andes to Aboriginal Australia have long described time not as a straight line, but as a layered or spiral reality, where the past and future coexist and interact with the present. For them, time is a multidimensional landscape to be walked, not a river to be sailed down. If a hidden dimension governing time were ever scientifically confirmed, it would not invalidate these ancient narratives, it would revitalize them, blending empirical knowledge with deep cultural wisdom. This cultural impact extends far beyond the screen or the sacred text, reaching directly into how we learn and understand the world. Complex ideas about quantum gravity and emergent spacetime become relatable when framed through the narrative of Doctor Who's TARDIS, a machine that is bigger on the inside, or the multiverse journeys in everything everywhere all at once. These stories act as conceptual bridges, translating abstract mathematics into emotional and sensory experiences that the public can grasp. The narrative power of the forgotten dimension helps close the gap between the laboratory and our lived reality, enriching our collective imagination and fundamentally changing how we envision our past, our present, and the vast array of possible futures that lie ahead. The next decade promises to push the boundaries of our vision, with experiments designed to finally see the unseen. The James Webb Space Telescope is already peering into the universe's infancy, searching for the faint imprint of cosmic strings in the ancient light. These hypothetical, unimaginably dense flaws in spacetime, if detected, would be a direct window into the high-energy physics of the early cosmos, potentially revealing the geometric scars of dimensional phase transitions. On the ground, plans are advancing for the future Circular Collider, a colossal machine with a circumference of over 90 kilometers. It would smash particles together with unprecedented force, probing energies where the subtle effects of extra dimensions or even microscopic black holes might finally become visible. Alongside these giant instruments, a quieter revolution is underway in the world of computation. Physicists are using artificial intelligence to navigate the labyrinthine mathematics of string theory and simulate the complex emergence of spacetime from quantum information. These digital laboratories allow us to test how a higher dimensional reality could project the familiar laws of physics and the arrow of time into our world. Leading theorists like Kamran Vafa suggest that within the next 10 years, we may gather enough anomalous data, perhaps from gravitational wave observatories or precision measurements of the cosmic microwave background, to point decisively toward a specific geometric formulation of the cosmos. A confirmed discovery of the forgotten dimension would trigger a paradigm shift on the scale of the Copernican revolution. Our most basic assumptions about reality would be upended, rewriting textbooks from the ground up and opening doors to technologies we can barely conceive. The mastery of dimensional geometry could lead to new forms of energy, or radical advancements in quantum computing that leverage the underlying network of spacetime itself. This knowledge will not remain confined to theoretical physics. The implications will ripple into cosmology, philosophy, and even computer science, forcing every field to reconsider its relationship with time and causality. Such profound power naturally carries ethical weight. If we begin to understand the very fabric of time, what responsibility comes with that knowledge? The next decade could be the pivotal moment where our persistent inquiry into the forgotten dimension transforms from a captivating mystery into a fundamental truth, forever altering our place in the cosmos. The power to understand time is the power to reshape existence itself, with the forgotten dimension potentially revealing the gears and levers behind temporal flow. We stand at the precipice of a profound ethical frontier. The ability to manipulate time, even in limited ways, would carry responsibilities far beyond any technology we have ever known. This is not merely about building a machine. It is about holding the fabric of cause and effect in our hands. The fundamental principle of causality is the bedrock of our reality, of justice, of memory, and of identity. Tinkering with it carelessly could unravel the very logic that holds our world together. The ethical parallels to the dawn of the nuclear age are stark. Just as splitting the atom gave humanity unprecedented power alongside existential risk, splitting the mystery of time could unleash forces we are ill-equipped to control. Physicist and ethicist Max Tegmark often warns that the first species to master time would hold the ultimate advantage and the ultimate weapon. Imagine a world where temporal insights are weaponized. An adversary could, in theory, create localized causal disruptions, rendering an enemy's command and control systems useless by making effects precede their causes. The economic implications are equally staggering. What if certain financial institutions could gain microseconds of foresight into market fluctuations, creating an unbreachable monopoly on wealth? The potential for abuse makes the current debates over artificial intelligence seem trivial by comparison. Yet, the potential benefits are equally breathtaking. If we could decipher the biological clocks written into our cells at a fundamental level, we might not just treat diseases, but reverse aging itself. Cellular entropy could be managed, curing neurodegenerative illnesses and offering radically extended, healthy lifespans. But this golden promise is shadowed by a dire question. Who would have access to such a miracle? The risk of creating an unbridgeable chasm between a timeless elite and a mortal underclass is terrifying. It could fracture humanity into separate species, one that experiences time as a malleable resource and another that remains subject to its relentless decay. This forces us to confront a deep philosophical choice. Is time a natural order to be respected? A river whose current we should navigate but never try to reverse? Or is it a frontier to be conquered, a final barrier to human mastery over the physical world? The answer will define our species for millennia to come. As with any transformative knowledge, the path forward demands a global conversation, one that includes philosophers, policymakers, and the public, not just physicists. We must establish boundaries for scientific intervention before the capabilities themselves emerge. The forgotten dimension offers a key, but it does not come with an instruction manual for its ethical use. This immense responsibility is the inevitable companion to profound understanding, a reminder that the greatest discoveries force us to look not just outward at the cosmos, but inward at our own wisdom and our values. The most profound discoveries are not made in isolation, but in the shared space of public imagination. We stand at a moment where the nature of time itself is being redefined, and this conversation must extend far beyond the walls of academia. When ideas about extra dimensions and emergent spacetime become part of our cultural vocabulary, they cease to be esoteric secrets and transform into tools for collective wonder. This is the vital work of science communication, turning abstract mathematics into stories that resonate with our lived experience, documentaries with stunning visual effects, podcasts that feel like intimate conversations, and museum exhibits that let you walk through a model of cosmic inflation are not mere entertainment. They are bridges built by skilled communicators who translate the language of the cosmos into something we can all feel and understand. The YouTube channel PBS Space-Time, for instance, dives deep into quantum gravity and Brane cosmology without sacrificing clarity, trusting its audience to grapple with profound concepts. Similarly, planetariums and science museums now feature immersive displays that visualize the warping of space-time or the holographic principle, making the invisible architecture of reality tangible. Neil deGrasse Tyson often speaks to the power of this engagement, arguing that scientific literacy is not about memorizing facts, but about cultivating a cosmic perspective. It is about understanding our place in an unfolding story so vast, it reshapes our sense of what is possible. Effective communication of these ideas relies on strategic tools. The most powerful is the analogy, a conceptual shortcut that links the unknown to the familiar, explaining curled-up dimensions as the circular cross-section of a long garden hose, or describing entropy as the inevitable shuffling of a cosmic deck of cards, gives the mind a foothold. Visualizations are equally crucial, transforming equations into dynamic animations of colliding branes or the pixelated emergence of spacetime. These approaches actively dismantle common misconceptions, such as the idea that extra dimensions are simply hidden places we could travel to, rather than fundamental geometric properties that dictate the laws of physics. By involving a diverse public in this dialogue, We ensure that the monumental implications of this research, from the ethics of time to the fate of the cosmos, are debated in town halls and classrooms, not just in laboratories. This broad engagement does more than demystify science. It plants seeds of inspiration. A child who experiences the awe of a black hole simulation in a museum might just be the one who solves the problem of quantum gravity decades from now. Our journey through the forgotten dimension has taken us from the melting of an ice cube to the very edges of reality. We have seen how the relentless arrow of time, from our fading memories to the expanding universe, may not be a fundamental river but a compelling shadow. It could be an emergent property, a consequence of our universe's position within a higher dimensional geometry. This hidden architecture offers a stunningly elegant resolution to physics' greatest puzzles, from the fine-tuned beginning of the Big Bang to the preservation of information in black holes. It suggests that the flow of time and the forces that shape our world are two expressions of a single, deeper truth, written in the geometry of dimensions we have yet to see directly. This is not the end of the story, but a new beginning. The search for this foundational layer of reality continues, driven by colossal experiments and quiet calculations, all fueled by a shared human hunger to understand the nature of our existence. The search for a forgotten dimension is spilling beyond the chalkboards of physics, seeding revolutions in fields as diverse as computer science and biology. Consider the challenge of a machine learning algorithm tasked with recognizing a face. The data for a single image is a point in a space with millions of dimensions, each representing a pixel's color and position. Navigating this hyperspace to find patterns is a direct application of higher dimensional geometry, a practical echo of the cosmic bulk. These algorithms, which power everything from recommendation engines to medical diagnostics, are learning to see in dimensions far beyond our own, optimizing their paths through abstract landscapes of information. In biology, the concept reframes the very timeline of life. Evolution is not a simple march up a ladder, but a branching exploration through a vast space of genetic possibilities, a multidimensional fitness landscape where species navigate toward peaks of adaptability. A forgotten dimension governing time could imply that evolutionary paths we see as linear were shaped by a deeper, geometric terrain, influencing the pace and direction of life's grand experiment. This interdisciplinary spirit is fueling remarkable collaborations. Neuroscientists and physicists are now working together to model consciousness. Could our sense of a flowing present be the brain's way of processing information from a vast, high-dimensional state space? Your stream of thought might be a trajectory through a neural landscape with more dimensions than we can conceive. A complex system creating the illusion of a linear timeline from a tangled web of causes and effects. Economists, too, are borrowing from this physics. They study how people discount the future, a time preference that shapes every financial decision. If our perception of time's flow is malleable and rooted in a deeper geometry, it could revolutionize our models of human behavior, explaining why we sometimes make choices that seem irrational from a purely linear perspective. Complex systems theory thrives on this multidimensional thinking. Whether modeling the spread of a virus through a social network or the stability of an ecosystem, scientists represent these systems as multidimensional networks. A collapse in biodiversity or a sudden market crash can be seen as a phase transition, a dramatic shift in the system state that mirrors the way our universe might have undergone a dimensional phase transition at the Big Bang. As network scientist Albert Laszlo Barabasi has observed, complexity often hides in the intricate connections between components, connections that form a hidden architecture much like the bulk of extra dimensions. This cross-pollination is driving tangible innovation. In quantum computing, the goal is to harness the bizarre properties of quantum bits, or qubits. Unlike a classical bit that is either 0 or 1, a qubit can be in a superposition of both states simultaneously. This is like a particle existing in multiple states at once, a phenomenon that may be intimately linked to the properties of extra dimensions. By manipulating qubits, we are essentially learning to process information in a higher dimensional computational space, promising breakthroughs in drug discovery and materials science that are impossible for classical computers. Even the art world is being inspired. Cosmologically informed artists are creating stunning visualizations and installations that attempt to convey the feeling of multidimensional spaces, making the abstract mathematics of string theory an emotional and sensory experience. This fertile ground between disciplines enriches our entire pursuit. The mystery of time is not a solitary puzzle for physicists to solve in isolation. It is a nexus where biology, computer science, economics, and art converge, each field offering a unique lens and receiving profound insights in return. This holistic approach accelerates progress, reminding us that the deepest truths about our universe are woven into a single, interconnected tapestry of knowledge. Close your eyes and recall a moment when time seemed to stop. Perhaps it was a breathtaking sunset, a sudden shock, or the quiet comfort of a loved one's embrace. In those instants, the relentless forward rush we call time dissolves into a single, expanded now. Your personal experience of time's flow is not a constant tick of a cosmic clock, but a river that speeds through tedious afternoons and slows to a trickle in moments of awe. This fluidity is the very essence of your consciousness, a psychological clock that ticks to the rhythm of your emotions. Studies in psychology reveal that when you are bored or anxious, your brain's internal timekeeper, likely centered in the basal ganglia and prefrontal cortex, seems to drag each second over hot coals. Yet when you are fully engaged in a state of flow, lost in a challenging task or a joyful experience, that same clock simply vanishes. Your perception of time is not a passive recording of reality, but an active construction, a story your brain tells itself based on memory, attention, and emotional weight. As we age, this story seems to accelerate. A summer vacation felt like an eternity when you were 8, but now whole years can blur together. This is partly because childhood is filled with novel, first-time experiences that your brain encodes in rich detail, creating a long and dense memory file. Adulthood, with its familiar routines, generates fewer unique markers, making the past feel compressed and swift. Mindfulness practitioners understand this intimately. By anchoring their awareness in the present moment, in the simple sensation of a breath or the sound of a bird, they can stretch the subjective now, creating a spaciousness that defies the clock's tyranny. This practice does not change the physics of time, but it profoundly alters our relationship to its arrow, offering a taste of freedom from its constant pressure. This deep, subjective reality is why time feels so personal. The forgotten dimension may dictate the cosmic rules, but your mind writes the daily script. Embracing this duality is not a contradiction, but an acceptance of a richer truth. The objective laws of physics and the subjective river of your life are two valid descriptions of a single, magnificent reality. Your journey, with all its memories and hopes, is not diminished by cosmic geometry, but is woven into its very fabric. This personal insight bridges the vast gap between the quantum and the quotidian, revealing that your most intimate moments are part of a dimensional tapestry of staggering beauty and complexity. We have journeyed from the melting of an ice cube to the edge of a higher dimensional reality, tracing the elusive arrow of time. We began with ancient puzzles, watching philosophers and physicists struggle with a universe whose fundamental laws are timeless, yet whose every moment is drenched in the irreversible flow from past to future. The clues were always there, hidden in plain sight. The relentless increase of entropy gave us a thermodynamic arrow, the expansion of the cosmos a cosmological one, and the stream of our consciousness a psychological direction. Yet each of these only pointed deeper, to a single haunting question. Why did the universe begin in a state of such exquisite order, setting this entire irreversible cascade into motion? The forgotten dimension offers a breathtakingly elegant answer. It suggests that what we perceive as the relentless flow of time is not a fundamental river, but a compelling shadow. It is an emergent property, a consequence of our universe's position and orientation within a grander geometric structure. This single idea has the power to unify our deepest mysteries. It reframes the Big Bang not as an absolute beginning, but as a transition within a higher dimensional bulk, naturally explaining the fine-tuned low-entropy start. It resolves the black hole information paradox by allowing information to be preserved holographically or within the extra dimension. It reinterprets dark energy as a geometric effect of the bulk's pressure on our brain. In this view, space-time itself is not the final stage of reality, but a shimmering illusion that condenses from a more fundamental, discrete network. Causality is not a primitive law, but a protected pattern that emerges from a geometric gradient in the hidden dimension, safeguarding logic and preventing paradox. This is more than a scientific revolution. It is a philosophical and cultural one, bridging disciplines from computer science to art, and forcing us to reconsider the nature of free will and our place in the cosmos. The physicist Carlo Rovelli offered a profound insight when he wrote, "Time is ignorance." Our powerful perception of a flowing now may indeed stem from our limited view, from our inability to see the full, timeless sculpture of reality from the higher dimensional perspective. We are like readers immersed in a single sentence of an epic novel, feeling the suspense of an unfolding plot, blind to the completed chapters that already exist. But this does not diminish our story, it enriches it. The quest to understand time is far from over. It is a living, breathing investigation that invites us all to participate. What are your thoughts on this dimensional key to reality? Share your reflections and questions in the comments below, and delve deeper into the mystery with the resources we have linked. If these journeys to the edge of understanding captivate you, subscribe for more, as we continue to explore the cosmos's greatest secrets. Each new discovery, each shared insight, brings us closer to unveiling the deepest architecture of existence.